Classical computers are everywhere. They help us write emails, play games, and even explore the universe. These machines use bits to process information. A bit can be either a 0 or a 1. This binary system allows computers to perform tasks by switching between these two states. However, classical computers have limitations. They struggle with very complex problems. For example, simulating large molecules, decrypting secure messages, or solving optimization issues can take years with classical systems. This is where quantum computers come in. They promise to solve these problems much faster. To understand quantum computers, we first need to know what makes them different. They use quantum bits or qubits, which can be more powerful than classical bits. This difference opens up new possibilities for computing. A qubit is the basic unit of information in a quantum computer. Unlike classical bits, qubits can be both 0 and 1 at the same time. This is because of a property called superposition. Superposition allows qubits to perform multiple calculations at once. Qubits can also interact in unique ways. When qubits become entangled, the state of one qubit is linked to the state of another. This connection exists even if they are far apart. This phenomenon, called entanglement, is key to quantum computing's potential. Building and maintaining qubits is challenging. They are very sensitive to their environment. Any disturbance can cause errors in calculations. Despite these challenges, researchers are finding ways to control qubits better. Qubits open the door to solving problems that are too complex for classical computers. But how do superposition and entanglement work? Superposition is a fundamental principle of quantum mechanics. It allows a qubit to be in a state of 0, 1, or both 0 and 1 simultaneously. Imagine spinning a coin. While it's in the air, it's both heads and tails. This is similar to a qubit in superposition. This ability to be in multiple states at once means a quantum computer can process a vast amount of information simultaneously. Classical computers, which process one state at a time, can't match this efficiency. This makes quantum computers potentially much faster for certain tasks. Creating and maintaining superposition is difficult. Qubits can lose their superposition due to interference from their environment. This is called decoherence. Scientists use advanced techniques to keep qubits in superposition for as long as possible. Superposition is just one part of the puzzle. Entanglement, another quantum phenomenon, adds even more power to quantum computing. Entanglement is a special connection between qubits. When two qubits are entangled, the state of one instantly affects the state of the other, no matter the distance between them. Albert Einstein called this spooky action at a distance. This instant connection allows quantum computers to perform incredibly complex calculations quickly. In classical computing, data needs to be transferred between bits, which takes time. Entangled qubits share information instantly, speeding up the process. Entanglement is not easy to achieve. It requires precise control over qubits. Researchers are developing new methods to create and maintain entangled states. This includes using special materials and cooling qubits to very low temperatures. Entanglement, combined with superposition, gives quantum computers their extraordinary power. But how can this power be used? Let's look at some potential applications in different fields. Section 5, Quantum Computing in Cryptography. Cryptography is the art of securing information. Classical cryptography relies on complex mathematical problems that are difficult to solve. But quantum computers could break these codes easily. This poses a risk to current encryption methods. However, quantum cryptography offers a solution. It uses the principles of quantum mechanics to create secure communication channels. For example, quantum key distribution, or QKD, allows two parties to share a secret key with absolute security. Any attempt to eavesdrop would disturb the quantum states and be detected. Governments and businesses are investing in quantum cryptography research. They aim to protect sensitive information from future quantum attacks. This is crucial for national security and financial transactions. Cryptography is just one field that can benefit from quantum computing. Let's explore how quantum computers could revolutionize drug discovery. Section 6. Quantum Computing in Drug Discovery. Drug discovery is a long and costly process. It involves testing thousands of molecules to find effective treatments. Classical computers can simulate molecular interactions, but the process is slow and limited in scope. Quantum computers can simulate these interactions much more efficiently. They can model complex molecules and predict how they will behave. This could speed up the drug discovery process and reduce costs. For example, quantum computers could help design new drugs for diseases like cancer and Alzheimer's. They could also improve existing drugs by optimizing their molecular structure. This could lead to more effective treatments with fewer side effects. Pharmaceutical companies are already investing in quantum computing research. They hope to use quantum simulations to develop new drugs faster and more cheaply. This could revolutionize the healthcare industry. Material science is another field that could benefit from quantum computing. Let's see how. Section 7. Quantum computing in material science. Material science involves studying and creating new materials. These materials are used in everything from electronics to construction. Classical computers can help design materials, but the process is limited by their computing power. Quantum computers can simulate the behavior of materials at the atomic level. This could lead to the discovery of new materials with unique properties. For example, superconductors that work at room temperature or stronger and lighter materials for aerospace. Researchers are already using quantum computers to explore new materials. This includes studying high-temperature superconductors and new types of batteries. These discoveries could have a significant impact on technology and industry. Quantum computing has many potential applications, but what is the current state of this technology? Let's find out. Section 8. Current stage of quantum computers. Quantum computers are still in the early stages of development. Most existing quantum computers are experimental and can only perform specific tasks. They are not yet powerful enough to replace classical computers for most applications. Researchers are making progress. Companies like IBM, Google, and Microsoft are developing quantum computers with more qubits and better error correction. These advancements are bringing us closer to practical quantum computing. However, there are still many challenges. Building and maintaining qubits is difficult, and quantum computers are prone to errors. Researchers are working on solutions, but it will take time. Understanding these challenges is crucial. Let's discuss some of the main obstacles in quantum computing. Section 9. Challenges in quantum computing. One of the biggest challenges in quantum computing is qubit stability. Qubits are very sensitive to their environment. Any disturbance can cause errors in calculations. This makes it difficult to perform reliable computations. Another challenge is error correction. Quantum computers need to correct errors without disrupting the qubit states. This requires complex algorithms and additional qubits, which increases the complexity of the system. Scalability is also a challenge. Building quantum computers with a large number of qubits is difficult. Each qubit needs to be precisely controlled, and the system needs to be kept at extremely low temperatures. Despite these challenges, researchers are optimistic. They are developing new technologies and techniques to overcome these obstacles. Let's look at the future potential of quantum computers. Section 10. The future of quantum computing. The future of quantum computing is promising. Researchers believe that quantum computers will eventually solve problems that are impossible for classical computers. This includes breaking complex cryptographic codes, simulating large molecules, and optimizing complex systems. Quantum computers could also lead to new technologies. For example, they could help develop new materials, design more efficient batteries, and create better artificial intelligence algorithms. These advancements could have a significant impact on many industries. Governments and companies are investing heavily in quantum computing research. They aim to develop practical quantum computers within the next few decades. This could revolutionize technology and change the way we solve problems. In conclusion, let's summarize the key points and the potential impact of quantum computing. Section 11. Conclusion: a new era of technology. Quantum computers use qubits instead of classical bits. Qubits can be in multiple states at once thanks to superposition. They can also be entangled, creating a powerful connection between them. These properties make quantum computers much more powerful than classical computers for certain tasks. They have potential applications in cryptography, drug discovery, and material science. However, quantum computers are still in the early stages of development. Despite the challenges, researchers are optimistic about the future of quantum computing. With ongoing research and investment, we may soon see practical quantum computers solving complex problems and transforming industries. Quantum computing represents a new era of technology. It has the potential to revolutionize the way we think about computation and solve some of the world's most challenging problems. The future is quantum.